Okay. So hello everyone, welcome to another UD Mobility Forum. Today we are it's our great pleasure to host Dr. Zhengzhong Tu from Texas A&M. Zhengzhong, Dr. Zhengzhong Tu is assistant professor of computer science and engineering at the Texas A&M University since last year. He received his PhD from UT Austin, and before joining Texas A&M, he actually worked as an AI researcher at Google Research. So he worked on generative foundation models for on-device applications. So he has published, if you check his publication, he has published a lot of papers in all kinds of top-tier journals, TPAMI, conference, NeurIPS, ICM, ECCV, all kinds of this conference. He has won a lot of awards, best paper finalist. I just will skip all of those. And today he will talk about the smarter, safer, trustworthy, connected mobility. I think it will be a very interesting topic. So without further ado, let's welcome Dr. Tu.
Yeah. Thanks, Dr. Gao, for the nice introduction. It's my pleasure to be here to share something we have done in the past, I think including 3 years. The talk title of today is Agentic V2X systems towards smarter, safer, and more trustworthy connected mobility. So I think quite a few of you already know what V2X is. But this talk I'll break into two parts. As you see, there are two video demos here. So the first video is something we'll be sharing about the so-called traditional V2X, or is actually the existing V2X, like based on features and machine learning models. We will share some of our works on addressing some of the challenges in the V2X system, including communication delay, interoperability, and system scalability. And in the second video is kind of a vision. I will explain further about what we call agentic V2X. So it's purely based on large language model, and we'll predict what will happen if we have everything equipped with this large language model. So my name is Zhengzhong Tu. And I first talk a little bit about myself. Yes, as Dr. Gao shared, I graduated at UT Austin. So after that, I worked at Google Research for 2 years. Since last year, I switched back to academia, assistant professor of computer science at Texas A&M. So my group name is called TACO. So I invented this name before before her last year. So it's called Trustworthy, Autonomous, Human-Centered, and Embodied Intelligence. So basically, we are interested in anything about generative AI, from visual generative models to these kind of large language model and agents. And well, of course, we cannot do any foundation model training, right? We're interested in how to apply these models, like including fine tuning, aligning, and also agentic applications towards interdisciplinary applications, such as the mobile devices, the VR headsets, cameras, and also autonomous vehicles and robotics. Okay, so I'll start with this very challenging driving scenario. We all drive every day. This is during nights. If you have a sudden blind spot cut, so it's very dangerous, even dangerous for myself, because it's very challenging for myself to drive at night as well. So you see that this scenario is actually this white car entered the blind spot, right? So the blind spot is actually at the right of your driving. And another very challenging scenario here. So we all believe that autonomous driving has been solved, but actually it's not, because there are so many this kind of like a long tail scenario. So there's an emergency. As soon as a police car have a flashing light towards you, and your eyesight will be largely shadowed by this glare. And even for human beings, very challenging. But you see that if you have autonomous vehicles, the glare of these lights will cause your perception models fail. So another example is also pretty challenging. So you see that there is a sequential accident here. So because there is a heavy haze, so you see that even there's a cluster of accident already happens. These people are waving their hand trying to stop, but the car just cannot really predict, right? Because they simply don't see that, and it's highway. So, and we have so many such scenario severe weather conditions, like especially in northern. I'm not sure whether in Delaware it snows or not. Maybe it doesn't snow. But in even northern, you see that the snow, heavy rain, haze will cause driving very dangerous if you don't. And this cannot really be solved by existing models because like there's always a trade-off, right? So driving has infinite number of long tail scenarios, corner cases, and the current existing models you cannot really capture the diversity of these scenarios. So I think there are so many things. Just to name a few here, and this very costly to let a single case accident happens because you probably see the cruise issue, right? Cruise have just accidentally have one accident that killed a pedestrian, and that's is enough to make the cruise company just go bankruptcy because like we have zero tolerance for these kind of scenarios. And autonomous driving now is entering a new stage of addressing all the long tail. So you can solve 99%, 99.9%, but you cannot really allow a single accident from happening. So we still have a long way to go to really kind of making a lot of progress to close a gap towards the last mileage in this problem. And as our transportation system is evolving, there is new emerging situations that we haven't seen before, right? So we need to keep working on that, maybe building more simulators, using V2X systems to allow communication to really push forward. So I think there's still a long way to go to how to position autonomous vehicles, driving algorithm perception into the whole transportation system and how to make everyone safer connectively. Okay. So yeah, so just I think we show some challenging scenarios. Yeah, of course, the companies like Waymo, Tesla, they are trying to make single vehicle perception models more safer and more robust. But there are some fundamental issues that cannot be really solved by single vehicle because there is a sensor limitations. And to this end, I think the US DOT is putting a lot of efforts to advocating this kind of so-called V2X system, vehicle to everything. So this is another view of how to solve the transportation challenges as a whole system, right? Because it's like a single vehicle is not really driving alone because there are many other vehicles, there is infrastructure, traffic lights, etc. And and the US DOT is putting a lot of efforts. I think last year they awarded 60 million towards the deployment of this V2X system, including one is received by Texas. So I think the Texas Transportation Institute is receiving 20 million towards a 5 year, some next a couple of years plan to do that. So I think this is an area that is flourishing, and there are a lot of emerging opportunities to work on this problem. So just do a little bit recap about what V2X is. So suppose you see this scenario. I just do a pause here. Yeah. So this is a very challenging scenario that I always use this demo to show why we need V2X. So you see that the ego vehicle is suppose is you are driving on the ego vehicle, and there is autonomous driving method to drive for that. Let's say that there is a truck here, right? So the blue circle truck. So this truck is blocking any of your sensor view. Even for a human, this is like a very challenging scenario. Your eyesight are all blocked by this truck. And then there's a red car that's running, violating the red lights, right? So you never see this because you believe on the traffic lights, but someone just break the law that's running the red light. So you never predict this happen. And if you keep driving that, you will hit the car and there's an accident happens. But what if you have the other two vehicles that can communicate with you? Because your eyesight is blocked, but the other vehicle can see that. And if you allow the communication between these multiple vehicles, then you know that there is a red car running red light. And then you can make a decision to wait for the red car to go pass through, and then the accident has been avoided, right? So very simple. Just from the system view, just allow multiple vehicles to share information, including perception, features, and then they allow you to have a shared perception across multiple vehicles that can potentially improve the whole system's perception capabilities because you can compensate each other's blind spots. Okay, so Throughout the past few years, we have all there seems to be agreement on like a V2X. We kind of fall into multiple categories. So basically, there are three categories from the perception perspective. Because I'm a computer vision guy, so we work mostly on the perception algorithms and etc. So we don't really go a lot of the real experiments in the real world. Yeah, we are bad at hardware. So we build this software from this. So basically, based on what you communicate, right? So there are basically three different categories. The very simple one is early fusion. Basically, you capture the raw perception data, like LiDAR point clouds, camera images. You directly throw this data to the other agents, right, connected with you. So you just share the raw perception data. That can cost a lot of bandwidth because a single LiDAR frame can cost maybe 50 megabytes, right? So it's very heavy, but it's very simple. You just get whatever you capture from the camera pipeline, and you transmit to others. And then the other one is called late fusion. Basically, if you just ignore all the communication system, you do the single agent perception using your own car, right? So basically, you get the LiDAR, you get the camera, and you do the perception, prediction, etc. You get the bounding boxes, segmentation map, and you finally transmit this segmentation or detection results with others. This can be very lightweight because a detection result only takes a few points, so axes, right? So just a few numbers. So you just need to communicate very few information. It's very fast. But you can imagine that this is maybe not very good because after you've done all the perception and only share the final prediction result, then what's the point of communication, right? So maybe you can do a simple voting, but you see that you are sacrificing a lot of intermediate kind of you have better way of fusing information together, better than the just communicating the final detection results. So there's one called intermediate fusion, which strikes a balance between these two, early fusion and late fusion. And there are a lot of papers, actually, more and more papers focus on intermediate fusion because there are many problems. So basically, the idea is that on each vehicle, you get the perception data, like a LiDAR frame or camera images, and then you do some encoding, right? You encode these features into some intermediate neural features that is heavily compressed, but also pretty representative of the scenario. And then you communicate those intermediate features into the vehicle you are interested in, and then you conduct a fusion among all the features, and then you do the final prediction. So this seems to be pretty, like ideally, this is a good way because you can control how much you compress, right? You can control what you how you compress. The encoder can be a ViT, can be something like a point transformer, etc. But you just retain the intermediate features that is presumably good representation features that is you can leverage them to do a bunch of the downstream tasks because maybe we are interested in some other task. But if you don't do these tasks in late fusion, we can never get the information, right? But there are many challenges. So it just seems to be pretty good, but this is always a trade-off, right? So if you can simply see that this intermediate fusion, you can easily go extreme to early or too late, right? If you bypass the encoder, then the encoder is simply a constant or it's kind of identity mapping, then you go to early fusion. If the encoder can do all the heavy lifting stuff and finally give you only a detection result, then it falls to late fusion, right? But in the intermediate range, you can really control how much you communicate and how much work you do on a single vehicle. But like we all see trade-offs. Like for example, if you do a lot of compress, then maybe you lose the kind of the transferability and the explainability because like you do all the things, you don't know what happens, right? So and if you just do little stuff, then the communication bandwidth is gonna be very heavy because like LiDAR frame is like a very big, right? We know that you learn autoencoder, you can compress features, but the compression rate ratio is a trade-off, right? If you compress more, you are losing more information. If you compress less, your compression ratio is very small. So you want to strike the right balance between you just need to have a very efficient communication, meaning that the communication, the feature that is compressed enough, while it also represent all the information you need for conducting the detection, collaborative detection result. Okay. And these are kind of the 5 pillars that we are interested in, but it's very hard to really solve all the issues in the same time. So the biggest challenge is really the communication bandwidth, and there some of the work is actually the first of the work to discuss these challenges, communication delay and noises, because like in communication, you can like a localization results is always noisy. So we're gonna account for this uncertainty during communication, because like I have to get the localization results of that agent such that I can project the features from that axis to my own axis, right? So that's if the localization result is noisy, how are I gonna compensate for that? So basically, we built, so there are even more challenges. Like if we talk about V2X, so it's not only V2V, so there's also infrastructure. So if you mount some sensor on the infrastructure, it's very high, right? It's on the traffic sign, around traffic sign or traffic monitoring camera. So the viewpoint of that sensor is different. You are kind of have a top-down bird-eye view. So how do you fuse this heterogeneous sensor data? Because like a camera, a vehicle view and the infrastructure view is very different, right? You have to capture this kind of heterogeneity when you design your model. And of course, there are some GPS localization error and asynchronization measurements, because once you receive the feature, it's not the current frame anymore, because it's kind of like if you have like a maybe 500 milliseconds delay, once you get the feature map, you request it, right? You request the time is ahead of that. So there is a temporal shift on the LiDAR frame that you are expecting. So you have to compensate for the delay such that you can do a reliable information fusion. Okay, so to solve this problem, we are still relying on a kind of end-to-end data-driven method. We want to capture this kind of noise in a transformer, and you just inject these kind of embeddings into a transformer and let the transformer to learn to offset this kind of noise, right? So because we run everything in simulator, you can simulate this communication delay. So in Carla, we have the synchronized simulation, even though it's not very realistic, but at least we can do that. We can capture this kind of uncertainty. And then if you simulate massive amounts of data and then you train this model, then this can hopefully learn to offset or compensate for this noise. So basically, we built actually the first transformer to in the V2X field to solve this problem. And this paper is also has a lot of citations. So this is a whole system. Basically, you have multiple vehicles like AV, Eagle, autonomous vehicle, and the infra. So this is a whole communication pipeline. We have ignored the actual communication system because we are mainly look at the algorithmic design. So it's so basically we capture each of the LiDAR data and then we rely on intermediate fusion. So we project using some point pillar encoder to project into some intermediate features. And then we transmit the features and gather all the features together in the Eagle vehicle. And we stack all the features together and use a single transformer to learn everything. So basically, you imagine that it's sort of like a video transformer design, right? Because we have 2D features, but we have multiple 2D features. And finally, we just stack together. It's like multiple frames of features. So it's very similar to a video transformer design. So we have 3 dimensions, 2D spatial features, and we have multiple agent feature. So the simplest way is to have 2 ways of fusion information, right? One way is to a spatial, like a self-attention. So similar to any vision transformer design. Another way is how to fuse the information across different agents. So here, then we design 2 types of attention because these features are pretty high dimensional. So it's hard to really have very basic self-attention to fuse everything in the same time because the dimension is very high. So basically, the first design is called the heterogeneous multi-agent self-attention. So basically, we account for the agent type, because we have two types of agent, right? Infra agent and we have the vehicle agent. So basically, we build a graph to represent the relationships between two other agents. So we have this kind of graph embedding the we have the infra to vehicle attention. We have the vehicle to infra attention, and you can say that we have different types of attention to account for that. So this is basically a very lightweight attention to just simply account for the heterogeneity in this V2X system. So another challenge is that this feature maps, lighter feature map is very high dimensional. So we cannot really use the vanilla vision transformer. So an efficient way is to use window transformer, right? Local transformer. So use local attention, which is introducing swing transformer. But here you see that if you simply use a single local window attention, it's not enough to capture, because sometimes if you have a large delay, you'll see that we stack the feature together. The vehicles are not in the same location, right? Maybe the vehicle just run away because it's very fast. You're driving very fast. So if you use single local window attention, you cannot really capture the same object in a small window, because the car have some 5 millisecond delay, may run very far away. So to capture this discrepancy, a synchronization in the feature map, we introduced a kind of multi-scale window attention. We increase the window size by 2x, larger and larger, to such that we can capture multi-scale. So if your car offset is large, we can use a large window. So, and this by using this multiple window, it can capture multiple latencies, right? So if you have a small latency, then you can use small window to capture that. So basically, we just use this parallel design, trying to let the transformer to learn what to use, right? So we just build this prior in this model and use data-driven method to learn everything end to end. Okay, so data. We also have built the first simulation data for V2X, which is a large scale data set at that time. It's called V2X set. So, and this is a training data. So we have included 5 different situations and many scenarios. And we have also made the agent a lot. So you see that in this ramp, in this entrance map, a ramp. So you see that there are many vehicles, because in simulator, we can make the scenario pretty challenging. And another very big challenge is the intersection. We also make a lot of agents here. So, and we simulate the data and generate all the perception data. And then we do the simulation. We do simulated latency. So basically you can sample a Gaussian from a Gaussian distribution from some latency and get the previous communication there. Okay, so this is called the noisy setting. So let's see how the performance. So it's first work. So we build the dataset simulation platform and then build a benchmark all the models. So I think one of the very big phenomenal V2X model is called the V2V So this is from the Uber labs, right? So one of the earliest work. So we test all the models by using the same training and the evaluation result. So this is only based on 3D detection. So you see that the performance is actually pretty good. So it advances in the perfect setting, the AP average precision 1.5 advances by 4.5%. And in the noisy setting, it's even the performance improvement is even bigger. Okay. So this is some sort of aberration study to show when the noise goes up, right? So we have positional error noise, we have the heading error noise, and we have the time delay. How does the performance drop? You see that all the models drop. That's like expected. But we see that if our model drops, actually compared to others, the drop rate is kind of smaller, because we have a transformer to capture the latency, and we learn how to compensate the latency throughout the embed using the time embedding. Yeah, you can say that the black dotted line is no fusion. So if you have too much error, so some of the fusion-based V2X is even worse than no fusion, because you get some noisy data, right? Very noisy data maybe is where affect in the negative way your single vehicle detection. Yeah. So this you see that some of the models just drop below the no fusion. Yeah, I think this is hard to see. So always hard to see these small detection results. Yeah, but you can check the paper. We have a lot of comparisons here. So this is a 3D detection result. You can see most of the vehicles are being detected, but some of challenging cases, you see that our model is a lot better than the others. So I will show this video here. So this is we benchmark multiple tasks, 3D object detection, road segmentation. So you see that this multi-vehicle fusion, the prediction of the road map segmentation is actually pretty stable. You'll see that it's very close to ground truth, right? I think we also had the video for 3D detection. I didn't show here. Okay. So just a quickly walkthrough of some of what we have done before. So this work, we focus on a different challenge. So basically, we're imagining this future. Okay. So far, we haven't talked about how to system design this whole V2X system, right? But if you see that so far, we only talk about single collaboration group. So because for the previous model, we assume that every model in every agent is the same and they are transparent. We can get the model weights, we can get the model architecture easily. But in the future, maybe we have different systems. Like you have the Tesla collaboration system, right? They may collaborate, but they won't be collaborating with other systems because they are not open sourcing their data model IP at all. Waymo has their own system, and maybe Delaware, we have the own collaboration system. So without exposing any model-based architecture, how do we allow the different system, heterogeneous system, to collaborate? So we think that this problem is very important because the US DOT, the government, of course, they want to promote every vehicle to collaborate as much as possible. But it's naturally not easy because every company have their own IP, right? They don't want to open source or release their model. So how do you make all the heterogeneous system collaborate without knowing the internal kind of thing? So what we build is actually is such a system that will allow you to do that, security. So basically, you have many local systems, right? That have Tesla Fusion and you have the Waymo Fusion. But we are kind of proposing this, maybe we can maintain a shared protocol that is maintained by the government. And this shared protocol can allow projection and reverting from any of the local things. So basically, we have a transparent shared protocol. And for any of the local features, I just need you to have a way, learn an adapter and reverter pair to be able to transfer your feature into the shared protocol and transfer back. So imagine in the real world, then how does it function? So I have a Tesla feature. I just need to transfer my feature into the government maintained shared protocol. And then all the features will communicate in that transparent layer. And then after collaboration, I will just pull the feature and go back to myself. So in this layer, you see that local feature, adapter, reverter pair, you can all make secure. It's not your own IP, right? But we'll do everything in this transparent layer. So we are learning this. The architecture is a little bit complicated, but we show that this kind of paradigm actually works. You don't need to really open source, and you can have different models. You can have your detection, segmentation network, some other network. They can all collaborate with each other. Yeah. So I think this is a kind of discuss the kind of system, how to make the system interoperable, right? So you can see that we actually show without this collaboration, you see that if you collaborate two simple networks, one do detection, one do segmentation, and they don't align, you see that the collaboration actually make it worse because like you see that there's a lot of noise, right? A lot of feature misalignment. And after our collaborative learning, we can see that the collaborative result is actually pretty good. So this is a result of one detection and one segmentation, and they don't know each other. So yeah, so we can make it work. I think that can really improve the system interoperability and transparency without letting all the individual groups to open source anything. Okay, so yeah, just a quick glance because actually there are many issues. I've been publishing a lot of works on to addressing each of the components. So basically, we have 2 IROS papers this year, which I cannot attend. I think it's in China. Yeah. So to solve this communication bandwidth, and we have like many work to solve the heterogeneity because there are different agent types, right? So we're gonna account for this heterogeneous fusion using some special type of transformer. So we also have solved this kind of system transparency because we want to allow different systems to collaborate in a secure way. So I think this work falls into the federative learning concept, but we don't go that way because we just discuss this problem standalone. Yeah, and we also have some scenario designs because we run everything in simulator. So then the scenarios in simulator is very important. So we need to do massive amount of simulation to account for different aspects in this simulator. But the issue here is that you see that it's always trade-off, right? It's very hard to address all the issues simultaneously. We always see trade-off. If you want to achieve one property and you are sacrifice some other things. So this actually inspired our something we called fall into the agentic thing. So we just present this called LangCoop idea. This is an idea paper in the CVPR 2025 workshop, and actually got the recognition by winning the Best Paper Award in this workshop. So it's a very, I think this is a very brave idea, but like we just want to show that or want to verify that can we do collaborative driving using natural language. So the thought process is like this. So we work on natural language like a large language model a lot, and you see that the large language model has the evolution from have single modality to multiple modality, right? You have introduced the vision or video capabilities, and then there is reasoning. You can do more and more challenging tasks such as coding, math, some of embodied applications. And now we have this multi-modal large language model that can really interact with the real world. So such as you have the vision language action model to enable these manipulations or some of the humanoid to behave, to take actions in the real world. And we also have the vehicles that maybe you can mount a large language model and the vehicles to interact, drive in the real world. And in autonomous driving, we have this history as well. The earliest is the modularized, like we have perception, prediction, and the planning, right? Or even control. So here we all meet the control part. So this system works pretty reliable because I think currently the working system in all the large companies, they are building a lot of the experts to deal with every aspect. And then after 2022, there is a UniAD. That paper is from, I think it's from Shanghai AI Lab. So they propose that using the individual modularized model, maybe they have accumulation error because each of the module is designed and trained separately, right? So if one model has error, it can accumulate and propagate throughout the system. And it's hard to optimize the whole system. They say that maybe we can make the modularized components to be differentiable everywhere. Then you can optimize the whole system in the same time, right? But it's still a modularized. They have perception module, prediction module, and planning module, and they have a token to communicate throughout the whole system. So such that you can do end-to-end training. And then with this, we began to see in this year, right, or last year, we see a lot of large language model works in this to do autonomous driving. I think one of the work like Drive VLM is from Li Auto from China. So there are a lot of papers from China right now to do this end-to-end driving using large language model. So basically, it's a trend now. So can we try something along this field? Actually, I think our group is so last year, from last December, so Waymo has released this paper called EMMA, end-to-end multi-modal model for autonomous driving. So they are using the Google's Party model. It's a multi-modal large language model to do end-to-end driving. So they show that it's better than, it's actually could achieve better result if you fine-tune the model. So right after that, we think that this field really needs open source effort, right? Because we are academia, the whole academia or some of the open source community, we need something to work with. And I don't think that Waymo is gonna open source the model. So we built this called OpenEMMA. So currently has a lot of stars. So we try to replicate the whole system like the Emma presented, using all the open source tools. So basically, we build this purely vision-based like a framework using COT, chain of thought reasoning, using some of the open source model like Llama 3.2 or Qwen 2, and we use some like a context, like we do some context engineering, right? So we first do the perception, then do prediction planning, and get all the context as a prompt to let the model drive end to end. So it's still a non-training framework because we don't have the resource to train, and I don't think that we have enough data set to train because Waymo has the infinite data set to train to make the model work. So we just want to show that it can work using all the open source thing. So how does it work? So you see that we try this model and we build this framework and test on the new things data set. You can see that the driving trajectory actually makes sense, right? So it's not 100% work, but at least in some challenging scenarios, it can generate reliable waypoint. At least it gives us, it offers open source framework for all the practitioners to really try and prompt. This is a night driving thing. You can see that it's also kind of makes sense, even though it's always driving straight. Yeah. So trying to make this vision line model, especially public vision line model, work on this task is not easy because, like, initially when we first build this model, the waypoint will go to the sky. The waypoint just kind of very random. So we have do a lot of like engineering work to make the waypoint normal. Yeah. So with this new kind of open source tool, we can try our collaboration with language, right? So before that, we don't even have a driving VLM that's open source that allow us to do this experiment. So build on that, we just leverage the single vehicle to have this kind of open AMR kind of end-to-end driving. And then we build this collaboration network that basically every vehicle don't have this kind of have this vision transformer, has a lot of modules, but only have one multi-modal language model, which is a VLM. And then we let them to communicate with each other. So what framework we build is called this kind of LangCoop framework. So we for each of the vehicle, we get the surrounding pictures by the cameras. And then we use a M3 COT, which is basically a more advanced version of the COT we built before. So basically we have this pipeline. It still follows the perception prediction planning. So we first get the scene description, and then we also get the previous waypoint and get the interactive objects. And also we also have the future intent description inside this framework. We use all these as a package. So it's called a language package, and then communicate the package with all the other things. So how does the package look like? So you can see that there are agent metadata, we have a lot of things. So basically we pack all the information, perception, planning, prediction, and the intent into a language format. So it's basically a JSON format, you can imagine that, or a dictionary. And to our surprise, or it's not a surprise, it's expected, this is going to be very small, right? It's purely language. So it's going to be less than 2 kilobytes. So less than 2 kilobytes, you can transmit many messages. Like you can transmit thousands of like codes. But if you have done that right, like you have described the scene in much detail, and then you can capture all the information in the picture. But using pure language, it's just a bunch of words and the axes. So this is very naturally like a very efficient in terms of communication, because previously we have to communicate features, and that's a big matrix, right? So if you can compress everything in language, the communication is by nature is very small. So basically this framework, the biggest benefit is that natural language is in nature very condensed because there are human knowledge. You like during drive, we also speak language, right? Because it's very efficient way of communicating information. And it's also very semantically rich, because imagine in the previous like a paradigm, you communicate features. If there's an emergency, how do you communicate the emergency accident to another agent? It's hard because you have to train some model to capture that information. But in language, we just say that, oh, there's an emergency surrounding me. Be aware, right? So that's easy to describe any scenario. So the semantic reach is something that the previous feature-based communication cannot really compare, cannot even compete with. So we draw something like there are different standard in V2X, the early DSRC, and of course the communication bandwidth is becoming larger and larger in like increasing. Imagine we have 5G, but we work on we are in Texas where we live in a small town, right? So there are many rural areas that you don't have the connection. So we use LTE, which is very unstable in many rural regions. So language is presumably as low as just communicating bounding box, because bounding box is also part of our information, right? And it's the most, if you want to really communicate many things, it's at most like a very lightweight neural features. Yeah, because like we just showed that using 2 kilobytes, you can communicate almost everything you need. Yeah, so it's very efficient as compared to other kind of raw data is like far beyond the maximum we can do. So if you have, imagine you have in future, you have many agents, using language is an efficient way and a scalable way. So another benefit is that it's also intrinsically like a support heterogeneous systems, and it's also easy to interoperate. So now we have many language models. So sometimes you use ChatGPT, use Gemini, right? But you wouldn't doubt that whether you can exchange these two models because they are all speak natural language. So imagine the previous word stamp we shared. We have different protocols for each group. But now, no matter what language model you're using, the output is always language, right? You can use ChatGPT in one vehicle. You can use Gemini. You can use DeepSeek in another vehicle. But all the output is formalized in language. So they are naturally interoperable. So, and what's even more exciting is that it's interoperable within humans, which I'll mention later. Yeah. So another benefit is that it's also pretty transparent, right? Because now we have the reasoning tool. You can simply ask the language model to tell you to export the reasoning trace, such that the human you can diagnose this trait. And in the feature-based era, it's hard because interpretable, you have to plot the heat maps in the feature and trying to do some explanatory work. But natural language, they're by nature explainable. And it's also explainable by human because you can simply ask the model why you do like this, right? Yeah, so I think this is something that we haven't get before, but imagine there's an emergency vehicle. You want to communicate, right? Or there's the hazy, imagine recall the hazy accident, all the vehicles are going to keep hitting in that cluster, right? So here, if you allow this vehicle to communicate, then they can say that, oh, there's accident beyond, just stop driving. Then this is kind of like a decision level communication, or like you have a higher level communication, right? You can communicate, there are some special things happening, there is a road construction, you can reroute. But previously, this kind of information is very hard to communicate using features. But natural language is naturally capture this semantic information. You can communicate some special, special scenario situations nature. And what's more even is like using language to communicate is by nature human-centric because we designed this transportation system for humans. And we must, so imagine the future, we are driving with autonomous vehicles, right? You are driving, autonomous vehicles driving, Waymo, Tesla, they are driving. So how do you make human drivers to work with machine drivers? So if the machine is a black box, I feel unsafe. But if the machine, they can speak and communicate, or that we see a lot of accident by Waymo in San Francisco, they stuck somewhere. We don't know why, it's blocked the traffic for many hours, right? But if they can tell why, the police can operate with the vehicle, can understand what's the issue here. And so far it's not the case, right? Because so far it's just stuck on the road for hours. So if we allow this to really have this capability, they can really solve many problems, like make it human-centric. Okay, so whether it's feasible, you will see there. So yeah, this is a very brave idea. We are just trying to see whether we can achieve this. But first in simulator. So we built the first simulator to allow running VLMs in each vehicle real time in Carla. So it's not real time, but Kara allows us to do synchronously. Yeah. So you see that what happens. So these are two views from two agents. You see that there's a kind of a complicated scenario. You see there's a vehicle. Yeah. Okay. Yeah, it seems that it can drive, right? It can avoid this, some of the agents and pedestrians. You can see their bicycle here, avoid that. So the driving is not very stable because so far the VLMs are not good enough to generate very good driving trajectory. It's hard to make it work. Another kind of scenario here, you see that the two vehicle driving as a coupe, right? So they are driving and dodge these accidents. I thought some of the bicycles, etc. Yeah, it's a little bit kind of fluctuating, right? Because so far the vision language model, they cannot generate coherent waypoints. So we are trying to solve this problem, but maybe using some traditional method, right? Using common filter, etc. Yeah, but so far it's You see that we simulate run. Oh, sorry, there's something happening. Yeah, I just yeah. Yeah, the simulator sometimes they just they have some weird things. Yeah. Okay, so we also evaluate this by using some of the driving score, route completion, some of the safety metrics because we want to do end-to-end simulation. So this is now we don't really care about perception. We want to show the whole system they can drive, right? So you can see that we evaluate naively and also naive testing without any prompt engineering and using the reasoning. And you see that using reasoning, the performance is largely boosted. So you have to use reasoning. We also tested a bunch of models. You see table 5, like GPT-4o is still the best model, right? Best performing model. And GPT-4 mini is also pretty good. So you see that there is a large gap between open source and closed source. And since we are using open source model, so it's hard just to close the gap by making this idea fully work pretty good. Okay. So with this, we just developed this idea in early this year, just a few months ago, and we think that there is a large promising feature if we kind of present everything in language based. So here is the kind of the vision photo we draw previously. So basically, imagine that in the future we have many agents, many vehicles. We have the construction area. We have the smart intersection. We have the smart infrastructure, right? And we also have the drones. If we mount everything in language, we can see that they can communicate very naturally, and also human or pedestrian or some of the police officer, they can also act as an important role in this whole system. Yeah, so basically, this is our kind of the vision about the agentic V2X system. Like of course, you can use different models, right? But it doesn't matter because we unify the communication protocol using natural language. Okay, so we come through the drones. So how to introduce the drone? So we also have a very recent work that trying to introduce the roles of drones into this V2X system. We call it Air V2X. This paper is currently under review. So basically, why motivates us? So I'm collaborating with another faculty in civil engineering at Utah University. So Utah State also get the funding, 20 million funding from DOT to advance V2X. But one challenge of that, Utah has a lot of mountains. So it's very, very hard for them to build infrastructure, right? You build infrastructure in the mountain area, that's gonna take maybe 10 years, 20 years. I don't know about the efficiency. So instead, we can use drones. Drones can be a lightweight alternative to replace infrastructure. And it has mobility, right? You can put drones anywhere. So based on this, we generate this simulation data by introducing the drone. So we have drones, infrastructure, and also vehicles, 3 different types of agent. And we generate massive data, training data for that. So we also have designed 3 different ways for drones because this differs from the infrastructure because drone can do a hover to monitor like a mobile infrastructure, right? And you can adjust the height. And also we can do patrol to do patrol around area. We can do escort. If you have a very important vehicle you want to protect, you can do escort for that vehicle. Yeah, so we have different types. We have different weather. So we do many benchmarks, many experiments in this paper. So including 3D object detection, semantic segmentation, and also we do a comprehensive ablation study to show that the drone is very important and critical to ensure the whole system. So basically, it's a data set and benchmark paper. So welcome to check out the paper and try your model to see how it performs. Okay, so this is the last piece of work I'm trying to think. It's currently under still work in progress, but I think that it kind of opens a new field. Like, so we talk about communication in language, and now large language safety is very critical, right? We all worry about where the language model is gonna be jailbreaked, it's gonna hallucinate. So there are many safety and security issues in language model. So we want to discuss in how the communication system, if we want to transmit something to another vehicle, what safety security issues in the communication system. So basically, we'll see that maybe you have disconnected in the transmission, you just lose the package, right? Or you have repeated, right? The agent is malicious. They want to give you false information, right? Fake information. Or they just inject some variable in this. They want to jailbreak you. So we do a comprehensive taxonomy about all the safety and the communication threats in the collaborative driving, no matter what map passage you use. So it's very communication related. So see that you can have disconnected information. We have the repeated information replay, and we also have the something like a false data injection. So the data injection is very closely related to jailbreak in natural language, because simply the vehicle, there are some malicious vehicles, they want to jailbreak the whole system, right? So we do this, we still are developing this, and we are trying to develop a benchmark to encompass all the different types of threats in this collaborative driving system. And then we also have built a system to do defense. So it's called agentic defense. So because there are different types, so we're trying to unify different types in the same framework. And I think that agentic framework with a large language model and to do reasoning and then call the different tools to solve the different questions. That can be a very effective way of doing of solving the whole full stack attack problems. Okay, so just demos. Yeah, so you see this is very interesting. You see, without under attack, you see that you hit the bicycle. The simulator is pretty fun. So sometimes you see that it's kind of weird, yeah. But you see that it's easy attack and let the vehicle to hit, to keep hitting bicycle, yeah. And with our defense method, you see that exactly the same scenario. You see, it can actually wait for the bicycle to pass through, right? You see that, it stopped, yeah. Okay. Okay, so again, I think this is a future work. Okay, so I think V2X, this kind of agentic V2X system, we have so many works that we haven't done because we just started the first few works, right? Trying to promote this idea of like driving with natural language seems pretty promising. So basically, there is a full guideline of the V2X message set. There are like multiple hundreds of pages. So we haven't really aligned with the standard, like what information you want to communicate. And now we have an easy way because we can directly translate the white paper into our language set, right? And you can easily encompass all the needed information stated in this SAE J2735. Okay. Also, like a human agent collaboration, I think that it's very easy for the vehicle to communicate, but we haven't done any investigation how to be more efficient, more transparent, right? So also, if we have a drone in this system, how to do agentic UAV, what bigger roles can the UAV play in this whole system? And then more things, right? Privacy, security, we just started off one paper still under development. And the efficiency, I imagine that someone will ask me whether it's feasible to mount a large language model, right? So maybe, so far, our simulator, one tick of the simulation takes about 10 seconds because the current language model will do reasoning and it takes longer. But I think this is not an issue because the whole world is pushing forward an efficient large language model. So I think imagine maybe we don't need to wait maybe more than 1 year. We will have efficient large language model that can reason within 1 second. That at that time, is fully feasible, and we can't wait at that time, right? We do all these works, prove that is effective, and then the whole world will make the whole things happen, hopefully. Yeah. And societal impacts, because we don't talk too much about that, but imagine we have so many robots that can reason, plan, and talk with you. What the world will be? I think that's going to be a very fun world. Yeah. So we have all the things driving together. They can all speak. So that can be pretty interesting to envision. Yeah. So I think that's pretty much all for my work. Thanks very much.
Thank you, Dr. Zhu, for this very interesting and insightful talk. Questions from our audience and also and talk from our online attendants. How many people online? Yes, 10. 10? 8 or 10.
Yeah.
Hi, thank you for the presentation. So I want to ask if in the intersection, so when you do like data fusion, so I saw like there's like multiple writers on the RSU on different sides. So like how do you like pick the target? So the vehicle that you want to do the data fusion. So it's like there might be a lot of vehicles in the intersection if you like do data fusion with all the vehicle sides. So there might be like a lot of copies of the infrastructure data. So like how do you pick like which one you want to do, or like you just do fusion with all the vehicles?
I think so far, that's a very great question. So I think so far, we don't have this problem. So current existing data set only include a few, 3 to 5 agents, like one infra and 2 to 4 different agents, vehicles. So far we just fuse everything. Yeah. So I think like if you think that some vehicles information is duplicate or is purely useless, then I think it correlates to our recent work about like whether we want to trust, right? Whether we want to trust the other vehicles. Yeah, I think maybe there's something that we can be more efficient. We can ignore some duplicate information. But I think that currently there is no work really discuss this. But it's gonna be a very good scalability and efficiency question. Yeah, I think it's worth discussion about that.
Thank you. And also like if like in the first demo, also like in the intersection to the green car and the red car, like how do you if you detect there will be like a potential accident, how do you like define like you like send the message to green car? How do you like locate the green car, like which car you're gonna send a charge to?
Yeah, this is also a pretty good question. So we got so in the whole system, right? So there are different. Basically, we haven't talked about the communication paradigm, like whether you do P2P or you do broadcasting. So actually, one of the early paper we submitted to CVPR, we got rejected because of this question. So they say that P2P is not efficient. But so far we just do P2P. We connect with everything. But this is of course not an efficient way because we are not system guy. So, but I think later on broadcasting is very good. Like for each of the agent, we just throw all the information to the cloud. And if you found this is exciting or something like that, you are just pick useful information. Yeah, that can be a very good paradigm for communication. But I think that all these questions haven't been answered by this field because so far people are kind of excited about building more fancy transformers, but they don't focus on something that really the headache in this field, because I think this V2X has a lot of system level questions and also communication questions, etc. But because we build this data set, so it's a computer vision data set. So the vision people, AI people are jumping in to get a higher scores and publish papers, but very few people really focus on the real bottleneck of the whole system. Yeah. I think we need a lot of questions, papers like what you mentioned to address this. Yeah.
Thank you. I got one.
Yeah.
Good, you have a whole day.
So it's like I saw like it has the open source